When most people see radar, it's a flat, 2D image, with reds and greens and yellows on a map, but beneath the surface, the radar is scanning the atmosphere in layers, slicing through the storms one elevation at a time. Special radar softwares and viewing instruments can stitch these roughly 14 or so-ish separate elevation scans together and allow for a true volumetric, three-dimensional view of whatever weather phenomena you happen to be viewing. Today, I'm going to use an application called GR2 Analyst. That stands for Gibson Ridge. They have a whole tool set, amazing for analyzing and viewing weather radar data, and I will be showcasing the 1999 and 2013 Moore, Oklahoma F5 and EF5, plus the El Reno 2013 EF3, which is the record holder for the world's widest tornado. So without further ado, I want to go ahead and jump right into it. I have downloaded all the events that I'm going to showcase today from the AWS archive server. I'll leave a link to that in the description along with a link to download this software, but I'm going to open it up right now and then quickly open up some files to start viewing. Again, all of these NEXRAD radar datasets were downloaded from the AWS archive server, and I will have a link to that in the description so you can download your own files, and if you have some software to open them and view them, you can do so. So what we're looking at here is the very start of the Moore, Oklahoma 2013 EF5. You can see this software plots the NWS issued warnings as they were issued on the map, and that is cool to kind of give some insight and context for what the storm was doing at the time. The rapid intensification exhibited by this supercell is uncanny. This thing grew from a small rotating storm to a violent EF5 within a matter of 10 to 15 minutes. That's unusually fast, even by Oklahoma standards. We're viewing this dataset from KTLX. That is a radar that was just recently upgraded months earlier to dual polarization. It captured one of the first crystal clear tornado debris signatures with debris lofted higher than 20,000 feet into the atmosphere. As I pan up in altitude, the different sweeps from this radar, you can see that structure, that debris ball at the bottom of the hook echo. It remains very separate from the rain core and the rest of this supercell, which I believe is why it gives such an amazing 3D volumetric view. You see, I open up this window and we're greeted with something really amazing to look at. The 3D volumetric view of this tornado stands out for a few reasons. For one, the radar was super close, only about 15 miles away from the vortex, giving an incredibly sharp vertical view. Another reason is the new dual pole upgrade, which lets us see debris lofted over 20,000 feet in the air, perfectly separated from the rain core. Add that in with the clean atmosphere and powerful updraft, and you get a crystal clear column of rotation and debris, one of the most detailed 3D radar captures of a violent tornado ever recorded. Few moments have ever shown the power of radar or of nature quite like this one. This dataset provides one of the clearest examples of EF5 tornado structure. Level 2 data enables detailed analysis of tornado dynamics and debris lofting, and these scans of the Moore EF5 provide one of the clearest examples of that. You can see the tight velocity couplets, debris signatures, and structure of the vortex at multiple tilts. The dataset shows how the tornado evolved along its path, including the vertical extent of debris lofted upwards of 30,000 feet in the atmosphere. It's just truly remarkable. So that was a pretty quick but detailed glimpse into the 2013 Moore, Oklahoma EF5, but I'm going to go ahead and load up this dataset from the same radar site, but it focuses about 11 days earlier, I believe, the EF3, which struck El Reno, and to this day holds the record for the widest tornado in the United States. This is the El Reno 2013 May 31st EF3. The main vortex of this tornado was documented to be 2.6 miles wide at its peak width. That is almost 14,000 feet. I couldn't make a video about this tornado without at least mentioning the fact that this is the storm that killed 3 veteran storm chasers. Tim and Paul Samaras and Carl Young all lost their lives in this tragic event. Right here around 6:20 p.m. is when it rapidly intensified to its max width of just over 2.5 miles. It's pretty scary that the tornado that holds the world record for largest tornado wasn't given an EF5 rating. Here's something horrifying to think about. This thing, once it reached max intensity and width, it was almost fully rain wrapped. Look how much I've got to file away the reflectivity just to be able to see it during these scans. That really kind of hints at the fact that this was impossible to see when it took place. It's really incredible to see the largest tornado in recorded US history through the eyes of this 3D volumetric radar software. I love this app because it lets you mess with things like the environmental lighting to change change the way the light refracts off the storm, and you can really make sure you're not missing any details. This little clip right here is very sped up, but it kind of shows the process of changing the reflectivity color palettes inside of GR2 Analyst and kind of what it changes inside of the volume renderer. Granted, you're still viewing the exact same data, but you're changing, obviously, how it looks, and that's always fun. Again, that was the El Reno May 31st, 2013 EF3, and now I'm going to open up the 1999 KTLX, once again, Moore, Oklahoma, or more popularly known as the Bridge Creek-Moore EF5. This is the storm where for a brief moment Doppler on wheels measured a wind speed of, I think it was 321 miles an hour in one of the subvortices of this tornado. That is the highest wind speeds on Earth ever recorded. To this day, it's insane to even fathom that. The strongest hurricane is 215 miles per hour sustained winds, so that is remarkable. Another cool thing I feel like is worth mentioning, this is the storm that had the first ever tornado emergency issued for any town, but specifically the town of Moore. I believe it was issued roughly 40 minutes before the tornado entered Moore, and despite the inevitable damage, it was a very successful warning. People heard that new terminology and they acted. It's really awesome this app is able to present you with something that is truly very accurate to what you would have seen. There are a few things that kind of change a little bit about what would be seen in real life versus what you're seeing in front of you now, but it's still better than just imagining. You know, we couldn't all be there, so the fact that we have anything like this is very awesome. One other thing about this storm and some others just like it, this is the first of 3 very large, very violent tornadoes that all followed almost the exact same path and struck Moore. The first being this storm in 1999 in F5, which is before the enhanced Fujita scale. The second was in 2003 in F4, also before the enhanced Fujita scale. And finally, the last, 2013, the EF5 Moore, Oklahoma tornado, which devastated the town one final time. It's an incredibly sad story. Back in 1999, the radar data was a lot lower resolution than what we have today. But with that being the case, it's still awesome that we can get any sort of seemingly high resolution 3D volumetric render, like what I'm showing you right now, out of a low resolution radar product from 1999. The software is goated. Truly. So those were the 3 storms that I said I wanted to showcase with this software, but I do have something extra for y'all who stayed till the end. I'm going to show a full volume scan. So again, it's got all the different altitude sweeps, but this time this radar is the University of Oklahoma's RaXPol mobile X-band weather radar. And we're looking at a scan from the EF3 tornado that occurred near Shawnee, Oklahoma on May 19th, 2013. It was part of a broader outbreak that impacted several areas in central Oklahoma, but RaXPol was out collecting detailed data on that specific tornado. A little off topic, but you see, whenever I view datasets from mobile radars in GR2 Analyst, I turn off the background satellite map as well as town names, and I change my color palette. This is all due to the fact that GR2 Analyst doesn't plot this data in the correct spot on the map, and I don't want to deal with it being in the wrong spot, so I just turn off everything that puts it in the wrong spot and I view it on a black background. This dataset is truly incredible. It is only one scan, but it is a full volume RaXPol scan, so there are 17 different altitude sweeps to take a look at. When viewing velocity, I swear you can see a couple different vortices inside the main circulation, and honestly, I can't even make sense of the structure of this vortex just by looking at the different altitude scans, but I can open up the 3D renderer and we get a pretty good idea of what this radar was looking at. God, this software is so impressive. Every time I play with this stuff, it just blows me away. I absolutely love this software. But going into a little bit of detail of what you're looking at, actually, obviously you're able to see something that resembles the structure of a large, violent, almost wedge tornado, but you're not actually looking at the cloud or, you know, the particles that make up that vortex. What you're looking at is the reflectivity, just like a normal radar, rain, anything that's in that tornado. But if the debris plume is dense enough, you will see the exact structure in the 3D volume renderer because the debris, the rain, everything is the shape of the tornado. So I've switched over to velocity product inside of the 3D volume renderer, and I spin around to the backside of this storm. Look at how the inbound and outbound winds perfectly wrap around themselves, just how you'd expect almost. It's mind-boggling, this technology that we have. And this software has been around for like 20 years, just to let you know, doing this exact thing. There's another really cool feature that I love using that comes with this software that I haven't really showed yet, and that is something called a storm slice. What you can do is click that button right there and drag a line wherever you want, and then move it back and forth, and it shows you what's inside the storm along that exact axis. It's really useful for seeing how high debris was lofted if you use it on top of a correlation coefficient product. You can see here we get about, I want to say maybe 14, maybe 15,000 feet of a solid debris drop. And even though this is more of a 2D view instead of the 3D volume renderer, you can still manipulate the 3D camera and look at this possibly from the side if you want or anything like that. But this dataset is really just super impressive. I love looking at these mobile radar datasets. The resolution that they capture in these storms is insane. Obviously, that's why they're out there doing it, but if you're somebody who loves analyzing weather radar datasets, getting your hands on some public mobile radar datasets is something that you definitely should look into. Well, I really hope you enjoyed this roughly 10 or so minutes of me displaying these different datasets in GR2 Analyst, starting with the 2013 Moore, Oklahoma tornado, and then going to El Reno that same year, and then back to 1999, the Bridge Creek-Moore tornado. They all produce beautiful 3D renders in this software. And then the RaXPol dataset to finish it off is really just something that I wanted to show off. But I plan on making more videos like this, so if it's something that you enjoyed, just leave a like and subscribe. Appreciate it.